Hello, in this podcast we're learning about water pollution. Our learning targets are to describe the causes of water pollution, and you should be able to also describe the effects of water pollution. What to do about it, that will be learning in another podcast. Now with water pollution, sometimes it can be dramatic and it can be from just one event. And two oil spills that were super dramatic in our history was the Exxon Valdez oil spill in Alaska and the BP oil spill in the Gulf of Mexico. And both of those tremendous amounts of oil was spilled, far more than the BP oil spill. And they both have had a tremendous effect on the surrounding ecosystems, as this clip shows you about the Exxon Valdez.
Just after midnight on March 24, 1989, a distress call went out from the supertanker Exxon Valdez.
Evidently, we get some oil, and we're going to be here for a while.
It was 12 hours before efforts to contain the slick began. And by this time, almost 11 million gallons of oil had gushed from the ship. When they finally arrived on the scene, crews deployed barrier booms to corral the oil, and oil-skimming ships to remove it from the surface of the sea. By the end of the first week, the slick covered nearly 100 square miles. Waves of weathered crude now smeared the coastline. This was to become America's most expensive industrial accident. Two months into the spill, the oil covered 800 miles of shoreline and reached 470 miles south into the Gulf of Alaska. Of the nearly 11 million gallons spilled, somewhere between 20 and 40% is thought to have evaporated. The state says that perhaps 13% was recovered. Exxon claims it was closer to 25%. This leaves at least 3.5 million and perhaps more than 7 million gallons unaccounted for. Where did it go? And what are the environmental costs of this unrecovered oil? The oil's immediate impacts were obvious and grisly. Sea otters were among the hardest hit in those early weeks. Some were poisoned by toxins in the oil, like benzene, toluene, and xylene. Many others succumbed to hypothermia when the insulating property of their fur was destroyed. Tens of thousands of birds were also killed by direct contact with the oil. And contaminated carcasses scavenged by healthy animals spread the toxins through the food chain. The bulk of the oil ended up on the shoreline, and experts predict that over the coming years, the harsh Alaskan weather will remove much of it naturally. But could oil that persists, most of it beneath the rocky beaches, pose a continuing threat to coastal life? In 1969, this salt marsh in Massachusetts was awash with thousands of gallons of fuel oil, spilled by a grounded barge a few miles off the coast.
This was all dead. All of this area was killed. Okay.
Although the marsh appears to have recovered, they've come to see if any remnants of the spill can be found.
Oh,
wow. That is oil.
it doesn't look oily particularly,
You can't see
But
anything.
but it's really fuel oil. There's no question about it.
You've smelled that often enough.
And you can see it on the surface of the water down there.
Yep.
The effects of an oil spill are dramatic and disastrous, one as big as the Exxon Valdez spill. And then in the course of a few years, most of the effects, most of the obvious effects, the things that the tourists are looking at now, will for the most part be gone. The remaining effects will be subtle, They'll be difficult to detect. It doesn't mean they won't be important, but they won't be readily obvious.
Usually, though, the water pollution is long-term and out of sight, and it doesn't become dramatic for a long time. An example of this is the Pacific garbage patch.
At sea, thousands of miles from any land, the vastness of the ocean is giving way to what some say is the largest garbage dump in the world.
Bottle caps, soap bottles, shards of plastic.
It's called the Great Pacific Garbage Patch. It's mostly plastic, which doesn't biodegrade. It just crumbles down into smaller and smaller pieces. The patch now spreads across millions of square miles in the Pacific Ocean. How far does it extend? It can't be too large.
As a matter of fact, it extends from just off the coast of California all the way to China. It's bigger than the continental United States.
Charles Moore made the shocking discovery in 1997 by accident while sailing the Pacific. He's been collecting samples of the growing garbage patch ever since. Some samples contain 6 times more plastic than plankton. It's been described almost like a trash soup.
It's like a minestrone that's out there, and all the little vegetables are different colored bits of plastic.
The garbage patch is caused by a series of currents in the Pacific Ocean, pooling what we all throw away. The currents create a circular effect, pulling debris from North America, Asia, and the Hawaiian Islands, and shooting it all into a graveyard of trash. 3.5 million tons of it. 80% is plastic, and it doesn't decompose. It stays as little plastic pieces for decades.
This is a final sample.
Moore stages regular trips back to the garbage patch for research. During his latest mission, he noticed an alarming new trend.
This is the highest plastic to plankton ratio we've seen, obviously. From this 5 years ago, now from a sample taken just this year, the quantities have gone up very dramatically.
More than doubling in 5 years. Moore says there's no reason to suggest it will ever slow down. And here's something new. Evidence that shows small fish are eating the plastic. So is it entering our food chain?
A fish like this, I've found 26 pieces of plastic, all different colors, inside one stomach.
Birds, too, are making a meal of it. Large quantities are found in their stomachs.
Water pollution is any physical, biological, or chemical change in water quality that adversely affects living organisms or make the water unsuitable for desired use. Water pollution can be put into 2 categories. It can be point sources or non-point sources. Point sources are where you can pin where the pollution is coming from one particular place, like what you see over here, where a factory is releasing the pollutants through a tube into the river. Non-point sources are ones where you can't pin it to a particular spot and where it's spread over a large area. For example, here would be a farm or a feedlot where the pollution is spread over a large area and it just washes into the ocean, or where all of these things that spill on there could be battery fluid, it could be oil from oil changes, or just leaks in cars, or anything, just washes into the sewers, and then, or not even into the sewers, it just washes into the ground and off into the river. So just to reiterate, point sources discharge pollution from specific locations. Examples of these are factories, power plants, drain pipes, sewers, and mines. Non-point sources are scattered and diffuse. There's no specific location of discharge. Agricultural fields and feedlots are examples. Also, atmospheric deposition, which is another name for acid rain. These are contaminants that are carried by air currents, and then they're deposited onto surface waters as rain, snow, or dry particles. And also plastic litter, as you saw in the Pacific garbage patch. Infectious agents from water pollution kill 3.2 million annually. And most of that would be, of course, in the developed world, most of it in developed countries, where 80% of the diseases are linked to water. This could be due to waterborne infectious agents, which could be things like cholera, which is directly related to bacteria that are in unsanitized water, or it could be malaria, where the mosquitoes that carry malaria spend part of their life cycle in the water, or through inadequate sanitation, which is what causes the cholera. The main source of waterborne pathogens is improperly treated sewage, which is close to cholera, and it could be from animal waste from feedlots and fields are also important sources of pathogens. And at least 2.5 billion people in the less developed countries lack adequate sanitation, and about half of these lack access to clean drinking water. Safety measures, and most of these we'll be getting into in the next podcast. Public water supply is purified, and also sewage is collected and treated. Sanitary practices when processing the food. Now, if the streams are overpolluted, they can clean themselves. Basically what happens is to the farm or feedlot, fertilizer or some other waste sewage gets washed into the river. What happens is upstream of that you have something here called the clean zone. You start off with dissolved oxygen, and dissolved oxygen is the main measure that's used for water quality. If there's more oxygen, that means that more organisms can live because they need the oxygen. And that's the orange line. So the dissolved oxygen is high. And then you reach the point source. Then you come to the oxygen stag and decomposition zone. What's happening over here is that the bacteria is eating up the organic waste because it's being decomposed. The things that can live there are quite different, and the difference is probably due to clarity and also because the oxygen levels are going down. And when the oxygen levels go down far enough, then you come to the septic zone. Fish are all gone. All that's left there are fungi, sludge worms, and bacteria. And the decomposition there is continuing. But then finally, all that pollution has been decomposed and is gone. So now the oxygen levels can recover because the bacteria there is gone. The fish that can survive under low oxygen levels, like the carp, the garden leeches, are the first to return. And then finally, it's up to normal levels. Then we have the normal clean water organisms, the trout, the perch, the bass, the snake, and the stonefin. And so untreated water is one of the main problems in development. Now we'll discuss water pollution in developed countries. This picture here was taken in Cleveland, Ohio, in the Cuyahoga River. I'm going to go over some basic pollutants that we find. And these are mostly found in the developed countries, but you can also find in the developing countries because some of them also have these industries too. Metals are found, like metals like such as mercury, lead, cadmium, nickel are highly toxic. That's where you find all of these on batteries. If you don't dispose of your batteries properly, you just throw them on the side of the road. You may just throw them in the trash, and the landfill is not accurately built to hold these metals. Then they will just wash into the groundwater or into the river. These metals are highly persistent, and they will tend to bioaccumulate in the food chain, covered by accumulation in a much earlier body. The most widespread toxic metal contaminant in North America is mercury, found in fish. 600,000 American children have mercury levels high enough to cause mental deterioration, and 1 in 6 women have levels high enough to harm a fetus. Major source of these are mines. Also, non-metallic salts are a problem. At low concentrations, what they can do is immobilized by irrigation and concentrated by evaporation. And the levels can be toxic to plants and animals. If you remember back when you took living environments, you saw the toxicity of non-metallic salts. Remember when you added salt water to the onion cells, you saw that the cells literally shrank, and that is a problem. Of course, if you also add salt to as well, that will flow too for the same reason. The water just gets the diffusion. The water just gets pulled out of the cells. So the leaching of road salts has a detrimental effect on many ecosystems. And in India and Bangladesh, there's also a problem with arsenic. Organic chemicals are a problem, especially in the Hudson River. Thousands of natural and synthetic organic chemicals are used to make pesticides, plastics, pharmaceuticals, pigments, etc. And the most important sources of toxic organic chemicals in water are improper disposal of industrial and household waste, runoff of pesticides from fields, roadsides, golf courses, lawns, etc. The problem in the Hudson is from PCBs. This isn't being added now, but General Electric has plants in upstate New York on the Hudson that when it was legal, they dumped a lot of PCBs, which is used in the electrical equipment. They dumped that into the Hudson. They dumped into the Hudson. PCBs are very toxic and they bioaccumulate. Because of that, the Upper Hudson is a Superfund site. Every parts of the Hudson, you cannot eat any fish that you catch, and anything here around New York City, there's definite limitation on how much fish you can eat that you catch in the Hudson, and also if you're pregnant, you can't eat any fish at all. And acid bases are also a huge problem too, especially from mined other sources, and acid precipitation. Acid precipitation, we covered that in the sediment is a problem too. 25 billion metric tons of sediment that is solid that will surface waters every year. They obstruct shipping channels, they clog hydroelectric turbines, smother fish eggs, block out lightning photosynthesis, though it can be beneficial in terms of building coastal wetlands and nourishing floodplain fields. Thermal pollution or heat pollution is a big problem too, and this is raising or lowering water temperatures from normal levels, and that can harm the water quality and aquatic life. Water solubility in water decreases as the temperature increases. Just think of seltzer water in terms of the solubility of air. There's carbon dioxide in that water. Take an unopened bottle of seltzer and put it in the refrigerator. When you take it out, there's a lot less air that comes out when you open it than it would be if the unopened bottle was warm, and that's because water can hold a lot more air dissolved in it when it's cold than when it's hot. So species requiring high oxygen levels are hurt by warming water. And we cause warming water by putting water in from power plants and other industries. And this problem is actually easily solved just simply keep the water in cooling ponds, and when it's cooled enough, then release the water. Now, as I mentioned before, oxygen levels measure the water quality. Biological oxygen demand is the amount of dissolved oxygen consumed by aquatic microorganisms, and that's used to test for organic waste contamination. Dissolved oxygen content is the measure of dissolved oxygen in the water. The effect of oxygen demanding waste on rivers depends on the volume, flow, and temperature of river water. Now, the sewage that goes into the water that causes oxygen cycle, the sewage basically is fertilizer. We saw earlier when we were discussing agriculture that you take the sewage in a sewage treatment plant and you turn that stuff into fertilizer. So when sewage goes into the water, it basically is fertilizer, and that can cause a problem known as coastal eutrophication. Now, an oligotrophic lake is a lake that's low in nutrients, and it is clear, as you can see in this picture right here. Now, when you add nutrients, these nutrients can be fertilizer, it can be sewage. One problem, which was a problem that was solved, would be actually soap, believe it or not. A lot of soaps would contain phosphates, and phosphates are things that algae love. They will start blooming and shading the plants below. So phosphates are things that cause coastal eutrophication, and because of that, if you look at the detergents that you use to wash your clothes with, they all say that they don't contain phosphates. The only detergent that we use today that contains phosphates would be for cleaning dishes, because you really can't clean the dishes in the dishwasher without the phosphates. You add these nutrients, you add fertilizer, add sewage, and also if the weather is hot, that's exactly what the algae need to bloom or really overpopulate. And they're going to first shade the plants below. These plants below will be shaded out, which means that they're not going to get the light they need for photosynthesis, and they will die. As they die, and also the algae don't live all that long themselves, they are producing more ones, but the ones that die will decompose. And bacteria will decompose them, will be using up the oxygen that's in the water, and that will kill most of the aquatic animals that you see in this picture here. And this is now a eutrophic lake. And in this situation here, at the very, very top layer of the water, there you've got life, but below that there's almost nothing. One place where you have a serious problem is actually not in the lake, it's actually in the Gulf of Mexico. If you look in the picture over here, this is a satellite photo, and the colors show dissolved oxygen. Where it's red, that's where dissolved oxygen is almost down to zero. This area is called a dead zone. Well, dead zone because so many things there are dead because the oxygen isn't there to support it. And in addition to this large dead zone, there's 85% of large lakes near major U.S. populations have this cultural eutrophication. And it's called cultural because our culture is what's causing it. There's also natural eutrophication, which occurs in all lakes. Sometimes on the AP exam, they ask people environmental costs and economic costs. And an environmental cost is one that affects the environment. So the environmental cost of eutrophication would be that the ecosystem erratically change. The fish all die, the shellfish all die because there is no oxygen. An economic cost would be something that affects jobs, something that affects money. When the fish die, when the shellfish die, if the shrimps die, that will affect people. That will affect people's jobs because people make a living by catching fish, by catching shrimp, and without the shrimp, without catch the fish, people will lose jobs. So, how is high water quality maintained in the developed world? How do we avoid more fires on the river, like what we saw before? We do that by passing and enforcing laws. And over here we have a table that gives a list of important laws in the United States that keep our waters clear. And the Cuyahoga River fire, actually, there was actually more than one fire. This occurred in the 50s and the 60s. And that one occurred, the one you saw there, that big one, occurred, I believe, in 1969. From that, in that picture reached everyone over the whole world, and that motivated the Clean Water Act of 1972. And that was passed under the Nixon administration. And yes, for the AP exam, you do have to know all of these laws, as well as many other laws and treaties for all the other units. Now we come to the concluding questions. Number 1, what is the difference between a point source and a non-point source? Number 2, how do streams cleanse themselves? Number 3, what is the main source of infectious agents in water? Number 4, how is water quality measured? Number 5, the photo of the Cuyahoga River fire was taken in 1969, correctly. Which law was passed to make sure that this did not happen again? That concludes this podcast, and I will see you in class tomorrow.